Atoms have protons, neutrons, and electrons. And we can infer the number of the protons, electrons, and neutrons from the following notation. Oxygen 17 has 8 protons because oxygen has atomic number 8 in the periodic table. It has 17 minus 8, which is 9 neutrons, because the superscript indicates the sum of the protons and the neutrons. So 17 minus 8 is 9 neutrons. The number of electrons is the same as the number of protons, which is 8. That is because the element is neutral. That means it must have the same amount of electrons as protons. The positive charges and the negative charges need to be the same. Potassium 39. Potassium is element number 19 in the periodic table, which means it has 19 protons. 39 minus 19 equals 20 neutrons are in this element. And the number of electrons, once again, is similar to the number of protons, which is 19. It has 19 electrons. Chlorine 37. Chlorine is number 17 in the periodic table, which means it has 17 protons. It has 37 minus 17, which is 20 neutrons. And once again, the number of electrons is similar to the amount of protons, which is 17 electrons. Now, is the number of electrons always similar to the amount of protons? The answer is no. I can have situations in which there's more or less of the number you would expect based on a neutral element. When the number of electrons and protons is not the same, we no longer speak of an atom or an element, we call it an ion. So let's look at several ways in which you can make an ion. I can do it in 2 ways. The first way to do it is to take an electron away from an element, like here. In this case, I have element X, any given element, and I take an electron away from it. That leaves the element in a positive state. It is now X plus, because I've taken a negative charge away from it. I can also take 2 charges away from it, 2 electrons. In that case, I would generate X2 plus, and so forth. We call this a cation. Another way to make an ion is to add an electron to a particular atom. For instance, I'm adding an electron to element X once again, creating X minus. The atom now is negatively charged. I can also add 2 or 3, and then creating an atom with a different charge, 2 minus or 3 minus. The negatively charged atoms are called anions. So there's cations and anions. Now, what is the most stable form, the ionic form of elements? Let's look at sodium and potassium. The most stable form of the ionic form of sodium is sodium plus. And for potassium, it is potassium plus. These both are cations. Calcium, however, its most stable form, its most stable ionic form, is calcium 2 plus. And barium also exists in its ionic form as barium 2 plus. Now, chlorine, on the other hand, its most stable ionic form is chlorine minus, which is an anion. It has an extra electron. Iodine also likes to exist in an anionic form, iodine minus. Oxygen, its most stable form in the ionic form, is oxygen 2 minus. And nitrogen, the nitrogen ion, exists as nitrogen 3 minus. Here's a list of very common elemental anions. You see here the anions of carbon, nitrogen, oxygen, sulfur, and so forth. The names of these ions have common names, so-called common names. The common name is defined as the root of the name of the element, for instance, carbon, and then adding the suffix "ide." So carbon becomes carbide. The carbon ion is carbide. Similar for nitrogen. Nitrogen becomes nitride, and oxygen becomes oxide. Now, we'll be using these elemental anions quite a bit in the remainder of the class, so it's good to memorize this list. Now, what are the charges of the ions? What defines what kind of charge a particular ion has? Let's first look at the elemental anions. The elemental anions can be found on the right-hand side of the periodic table. They're indicated here in blue. These are the so-called non-metals of the periodic table. Let's first look at carbon. The last two electrons in the electrical configuration of carbon are in a 2p subshell. Now, if I add 4 more to it, 4 more electrons, that means that I'm filling up the 2p subshell. I am actually creating a closed shell arrangement, which is the same closed shell arrangement as the one for neon. In the process, I've generated a carbide ion, C4-. 4 extra electrons were added. Oxygen has 4 electrons in the 2p subshell. If I add 2 more, I once again create a closed shell arrangement. And in the process, I generate oxygen 2-. Oxygen 2- has an electron configuration which is similar to neon. Chlorine has 5 electrons in the 3p subshell. If I add 1 more, I create a closed shell arrangement. In the process, I generate a Cl- ion, chlorine minus. And the chlorine minus has an electron configuration which is similar to argon. So, the charge of the anion is defined by how many electrons have to be added to generate a closed shell arrangement. Let us now look at the cations. Cations come in 2 types. The first type is type 1. Type 1 cations have only one oxidation state. An oxidation state is, in the case of an ion, the same as the ion's charge. Let's look at lithium. Lithium has the following electron configuration. It has 1 electron in the 2s. Now, if I take this 1 electron away from it, that means I generate a closed shell arrangement and the lithium plus ion, the lithium plus cation. Sodium has 1 electron in the 3s. If I take 1 electron away, I generate, again, a closed shell arrangement and the sodium plus ion, the most stable ionic form of sodium. In the case of magnesium, where the electron configuration has 2 electrons in the 3s, taking these 2 electrons away will generate magnesium 2+ and, once again, a closed shell arrangement. So, the first 2 columns of the periodic table to the left, which are called the alkali metals and the alkaline earth metals, their ionic forms follow the following rule. It is defined, the charge of the ion is defined by how many electrons need to be taken away to create a closed shell arrangement. Now, beside type 1 cations, there are also type 2 cations. Type 2 cations can exist in multiple oxidation states, which means the ions can have multiple charges. Let's look at iron, for instance. Iron can exist in 2 oxidation states, which corresponds to iron 3+ and iron 2+. The oxidation state of the first is 3, the oxidation state of the second is 2. We indicate this by iron 3 and iron 2. The Roman numeral indicates the oxidation state of the element. Copper exists also in 2 oxidation states. It can exist as 2+ and 1+. That is copper 2 and copper 1. Lead can exist in 2 oxidation states as well. Lead 2+ and lead 4+. Indicated here by lead 2 and lead 4. So let's finish this segment by doing the same exercise as the one we did at the very beginning of this segment. Let's look at oxygen 17, 2-. This is an anion. And let's find out how many protons, neutrons, and electrons this anion has. The number of protons has not changed. It is defined by the element itself, the atomic number of the element, which is 8. So it has 8 protons. The number of neutrons also has not changed. It is 17 minus 8, which is 9 neutrons. The number of electrons has changed, however, relative to neutral oxygen. It has 2 extra electrons. The charge is 2-, which means 2 extra electrons. That means 8 plus 2 equals 10 electrons in total in this anion. Iron 57, 3+. Iron is number 26 in the periodic table, which means it has 26 protons. 57 minus 26 equals 31 neutrons. Now, this ion misses 3 electrons relative to its neutral form. That means 3 electrons are missing. The neutral form would have 26. So it's 26 minus 3, which equals 23 electrons for this cation.